Okay, so I hope I'm audible. Can you all hear me?
Yes, ma'am.
Yes, okay. So, and the screen is shared, I hope. Right.
Yes, ma'am, the screen is visible.
Okay, good. So, yeah, yesterday we just started off with the PCA approach in machine learning. So, the idea we were talking of is like you have a set of data points in some dimension and you want to get a lower dimensional representation of the data. Okay, and there are a lot of advantages to this. One is, of course, like you need to, in terms of storage, you don't have to store a lot of information. And the other thing is, many times a lower dimensional representation is, conveys more things, and there are definitely advantages of it. Okay, so we were looking at this, one illustrative example where you have a set of points, and perhaps always the best thing may not be a subspace, but an affine space is what gives you a better picture. Like if you want to project onto a lower dimensional space, maybe it's an affine space always. But an affine space is just a subspace which is translated, a subspace like this, which is moved so that the origin becomes, a different origin. So this point here becomes the origin. So what we said is we will focus on finding a subspace. Okay, and we'll try to project our data onto the subspace in such a way that there's some good properties that are maintained. Okay, so in just to formalize this a little more, so what we have is the original data set consists of all these points. So there are n points. Okay, so I'm just writing this as DO to O to denote original. So DO consists of these points x1 O up to xn O. Okay, so there are these endpoints. So these are all vectors and they are in d dimensions. Okay, so this is a vector of size Rd. Each of these is a vector of size Rd. Okay, so first thing you do is so that you want to focus on subspaces, you move the origin into the mean of all these points. Okay, so the mean of these points is just sum of all these divided by n, the number of samples or the number of points. Okay, and then what you do is you try to recreate these points, but now with respect to a mean center, so that the origin is actually the mean. Okay, so then that would be a new data set, so new revised data set, let me call it. Okay, new revised data set, which is again a set of n points. But now each of these points are, x1O, the original point, minus x bar. And x2 is x2O minus x bar. So you just displace it about the mean so that, this is the new axis. So these are, it's the same points, but the representation is such that you just remove the mean from it. Okay, so again, these points are still in the d-dimensional space. Okay, you've just subtracted out the mean. Okay, so now what PCA does is you want to find the best lower dimensional subspace, and you want to project these points, these revised points, onto the subspace. So now the subspace will, it's fine. It can pass through the origin because the origin is just the mean. Okay, and so that's fine. So our focus will be on finding the best lower dimensional subspace that can be used to represent the data. So let's just get into this idea of what a projection means. Okay, so suppose you want to project a point onto a lower dimensional subspace. Okay, so what does this really mean? So all of us know what a subspace is, right? So we've seen this in in our preliminary classes, and also you would have seen it in your linear algebra class. So basically a one-dimensional subspace is just a single vector. Okay, so this is a one-dimensional subspace. So it's basically this set of all any vector which is parallel to this one vector. Okay, so that is a one-dimensional subspace, and what you need to represent this subspace is just the single vector. Okay, so so this is the idea of a lower dimensional subspace, and you have like in multiple dimensions, and what you need for a subspace is a set of k vectors, okay, which are the basis for the subspace. And so in particular we assume, we use only orthonormal basis. So orthonormal is the set of vectors which are orthogonal to each other, and they have a length 1. Okay, so just to take an example, let's look at R3. Okay, so R3 is the whole vector space, and an orthonormal basis here is an example is the standard basis, okay, which is just 1 0 0 0 1 0 and 0 0 1. Okay, now any point you take, say something like 2 3 5, this you can represent using each of these vectors in the basis, right? So that's what a basis is. So it's just 2e1 plus 3e2 plus 5e3. Okay. So this is a representation in terms of the overall basis, the overall space. So R3, so every basis has a dimension of 3. Okay, so there'll be 3 vectors with which you can use to represent any point in R3. Okay, so now suppose I'm going to consider this subspace W1, which is constructed using just this vector E1. Okay, so W1 is just the span of E1. So the original space was something like this. So you have, these, it's a 3-dimensional space. So this was x1, x2, and x3. Okay, and so E1 was in this direction. So this was a unit vector in this direction. This was E1, this was E2, and this was E3. So now the span of E1 is just everything on the x-axis, the x1 axis. Okay, and what is the dimension of this space? What's the dimension of W1? Can you tell me what's the dimension of W1? Okay, am I audible?
Yes, ma'am.
Yeah, so can you just tell me, like, I'm considering W1 as the span of E1. So E1 is this vector 1 0 0. So what's its dimension of the space?
1.
1, right? Okay, so now if I want to project this vector 2 3 5 onto W1, the projection is just 2E1. So projection of 2 3 5 onto W1. So the projection of 2 3 5 onto W1. So that is just the nearest vector. So if you consider all the vectors in x1, in the x1 space, in this W1 space, what is the one that's nearest to this 2 3 5 vector? So that will just be 2 0 0. Okay, so in fact that is just 2e1. Okay, now another thing is, if you take W2, another subspace, which is this E2 vector, so everything along the x2 axis. Okay, so this one also has a dimension of 1. Okay, it's like the other case. This is one vector which is used to represent it, and the projection of 2 3 5 onto W2. So the projection of 2 3 5 onto the space onto W2, this is just going to be 0 3 5. 0 3 0. Okay, so 0 3 0. So this is just 3e2. Okay, so what you're doing here, in some sense, when you take the projection, is that you're looking at the subspace that you're considering is one of the the span of one of these subsets of these orthonormal bases. And then when you're trying to find a projection onto this, what you're taking is you're just looking at those components. So if you're projecting onto W1, you're just taking this part. If you're projecting onto W2, you're taking only this. Okay, now suppose you're taking the span of E1 and E2. So basically both this x1, x2 axis. Okay, so this is another subspace. So what is its dimension? Okay, are you all with me?
Yes, ma'am. Dimension of W3, ma'am, right?
Yes.
It would be 2.
It's 2, right? So yeah, so this is a small, so all these are smaller dimensional subspaces, and the projection of 2 3 5 onto W3, right? So this is what is the nearest vector in this x1, x2 plane, right? Um, are you all able to hear me?
Ma'am, it buffered a little in the middle, but it's fine now.
It's fine. Okay. Okay. So, yeah. So, yeah. So I'm just trying to do what we're doing now is a projection onto W3. Okay. So W3 is just spanned by E1 and E2. Okay. These two vectors. So what would the projection onto this be?
2 comma.
Can you say it again?
2 comma 3. 2 and
Yeah,
3.
so 2, 3, and actually 0 if you want to represent it as a subset of the, in 3 dimensions itself, you want to write the vector. So this is just 2e1 plus 3e2. Okay, so so this is the, when you look at projections, what you do is, one way to do it is you think of the overall orthonormal basis. Okay, and then each subspace you can think of as it is represented by a subset of this orthonormal basis, and then you just look at what are the components corresponding to those vectors. So in general, suppose you have any orthonormal basis. So what we took here was the standard basis. So in general, if you have any orthonormal basis, U1 to UD, so if it is a d-dimensional space, Rd is the original vector space. So any orthonormal basis has to have d vectors. Okay, and so consider U1 to UD, and if you have, so now any x in Rd, you can represent it using these orthonormal bases, and suppose you call these coefficients in this manner. So x is alpha 1 U1 plus alpha 2 U2 and so on up to alpha d UD. Okay, so a way to find alpha 1, alpha 2, alpha d, that is what we'll just see once. So remember U1 to UD are all orthonormal. So now if you take the dot product of X transpose U1, okay, so when we say that these are all orthonormal, what it means is that norm of all these vectors is 1, or UI transpose UI is 1, and ui transpose uj equal to 0 for all I not equal to j. For all the pairs, you have this. So this is what is the orthonormal basis. A set of orthonormal vectors is this, and there are d of them. Okay, so now to find this alpha 1 to alpha d, okay, what you do is you just take the dot product, so x transpose u1. So what this will give is, what's it going to give? Can you tell me?
Alpha 1.
Alpha 1, right? So all the other terms cancel out. So actually it's alpha 1 u1 transpose u1 plus alpha 2 u2 transpose u1 plus so on. Okay, plus alpha d ud transpose u1. And all these quantities are 0. Okay, so we are left with this, and u1 transpose u1 is anyway 1. So this is what you get. So in this manner, all the alpha i's is just going to be x transpose ui. Okay, so that's how you would represent, if you're given any orthonormal basis, the way you represent any vector x is just using these coefficients, which are computed in this manner. Okay, so I think this is probably stuff that you've already seen. Okay, so now when you look at projection onto a subspace, okay, so U1 to UD is the orthonormal basis, that you're considering, and suppose that's given, and you're in particular looking at a k-dimensional subspace, okay, and which is spanned by the vectors U1 to UK. So this U1 to UK is a subset of this original orthonormal basis, and you're looking at a projection onto such a subspace. Okay, so then so x is alpha 1 u1 plus so on up to alpha d ud, where the alpha i's were computed in this manner we just saw. So the projection x tilde, okay, so this is just going to be summation alpha I ui, where I is equal to 1 to k. Okay, so this is the projection onto W. Okay, so these alphas are the same alphas. So this is just going to be X transpose Ui times Ui. Okay, so this is the coefficient that you will get. Okay, so I hope this idea is clear. Okay, so please stop me if there are any questions on this. Okay, yeah. So can I just get a yes, no if things are clear or not? Yes. Yes. Okay. Good. So let's just move ahead. So the idea now is, so what we just saw so far is, suppose you're given these vectors u1 to ud, an orthonormal basis, and a subspace, which is given by the subspace, which is described by the subset of the orthonormal basis. Then how do you find the projection? Okay. So now the task in PCA is you also want to find these vectors u1 to uk. You want to find the best subspace so that the D, I mean, not to span D, but to represent D in the best possible way. Okay, so that I'll just come to what it means in the best possible way. So this is the problem. So what we saw is, if you're given the vectors u1 to uk, you know how to find a projection. But now the focus is on finding these u1 to uk's themselves. Okay, so instead of just looking at u1 to uk, what we will do is we'll try to think in terms of the orthonormal basis itself. So instead of finding the best subspace here, we are in some sense going to look at the orthonormal basis and view this subspace as a subspace of the orthonormal basis. Okay, so that's what we're going to do. So in some sense, we are going to find u1 uk as well as uk plus 1 and so on up to ud. Okay, so because once we know this, we have the best way of computing this subspace. I mean, we have a way to compute the projections onto the subspace. Okay, so again, these points D are given in this manner, x1 to xn.
Small question. So basically,
Yes,
what
Satya.
we are saying, yeah. So what we are saying is, we want to find on a subspace, and that subspace is basically going to be spanned on u1 to uk, right?
Yes,
So,
yes.
but instead of trying to find w directly, you consider any general orthonormal basis, find out what is the projection, and find out some kind of a metric over which you will optimize this.
Yes, exactly.
Okay.
Exactly, that's the idea. So the essential principle here is, because we know that every subspace can be extended to form a basis for the overall space, overall vector space. Okay, so if you have a subspace u1 to uk, there is a basis. There is an a set of vectors u1 to ud, and which this forms a part of it. You can extend it to form a basis. So we're kind of using this idea here. Okay. Yeah. So, so again, let's come back here. So the data set is given as x1 to xn. Okay, and so each point x1 is in xi is in Rd. Okay, so xi can be represented using u1 to ud, any orthonormal basis, which is, these u's are something that we are going to find. But given a u, you can write it in this manner. Okay, so alpha ij's represents the coefficient for the vector xi, I mean, corresponding to this uj vector. Okay, so it's the sum alpha ij uj, where alpha ij's is just computed in this manner, xi transpose uj. It's just the projection onto each of these vectors uj's. Okay, so that's how you compute alpha ij's, and this is the representation. So xi is just this. Now, if you're going to project onto u1 to uk, which is again a subspace. Okay, so what it means is that xi tilde, so the projection is just, you're going to use the first k vectors. Okay, so mind you, this is not the first t, but the first k vectors, and these alpha ij's are going to be same as in both these representations. Okay, so that's about the projection. So this is a lower dimensional projection, and again xi tilde is also an element of Rd. Okay, but it's just that it lies within W. Okay, so xi is in Rd and xi is in the subspace. Okay, so I'm using span and the subspace very interchangeably. So I hope, I think that should be clear. Okay, so now what we have is two things. So this is the original point, okay, represented in terms of the U's, and this is the projection. Okay. So what you want to do is you want to find these U1 to UDs so that these are orthonormal. So what it means is that I transpose UI is 1 for all vectors, and UI transpose UJ is 0, okay, for all I not equal to j. You want to find these orthonormal vectors, and there are d of them. And you also want to find them in such a way that this error, so this difference between this xi and xi tilde, that is as low as possible. Okay, so that is a metric that we are going to use. So this is one view. Okay, so this is one view of PCA. Okay, now instead of minimizing the error in projection, another thing is to maximize. There's another view of PCA where you try to maximize the variance in the projection. Okay, variance in the ultimate projections x bars. Okay, so this set. So x bar I. So this is I for all the data points. You want to maximize the variance in this. So this is another view. Okay, so these are actually complementary views in some sense. Okay, so what I will focus on is this first view. Okay, so you want to minimize the error in going from xi to xi tilde. Okay, you want to minimize this to the extent possible. Okay, so yeah, are there any questions till here? Shall I proceed with the formulation or just?
So there is one clarification. So for every x which was x1 to xd, now you are going to have alpha 11 to alpha 1d. 1k, right? Alpha 11 to 1k.
Yes, so this one, right?
Yeah. So
yes.
for example, the first training point will be alpha 1 all the way till alpha 1k. So there is k dimensional.
Yes.
Whereas originally it was x1, x11, x12 up to x1d.
Yeah, let me just write it. So x1, the first data point you take, this you can write it as alpha 11 u1 plus alpha 12 u2 plus so on up to alpha 1k uk. Okay, so this is in the projected space. Now in the original space, it was x1 was just alpha 11 u1 plus alpha 12 u2 plus so on plus alpha 1k uk, and also the remaining terms alpha 1k plus 1 uk plus 1 plus all the way till alpha 1d ud. Okay, so in representing the projection, you're using only the first k vectors, and so those coefficients as well.
So this is in terms of the basis u1 to ud that you provided, but in terms of original standard basis, it will be x11, x12, x13 up to all the features as it is.
Yes. So yes, exactly. So x1. So this is just x1, the first element, x12, and so on up to x1d. So this is the usual representation we take. So for example, like this 2, 3, 5 that we had. So the x1, it's going to be given in terms of the standard basis, this 2, 3, 5, and this u1 to ud, that could be some other basis, maybe something like 1, maybe 1 minus 1 0, and maybe 0 minus 1 0, and maybe 0 0 1. This can be another basis. Okay, so
provided it is orthonormal.
Yeah, these are not orthonormal, right? So this will be 1 by 2 or something. Yeah. So I think these are not orthonormal anyway. So yeah, basically these have to be orthonormal too. So maybe minus 1 1. something of this form. Okay. So yeah, so only thing that's changing is this representation U1 to UD. Instead of the standard basis, you're going to now find some other basis. Okay. Yeah. Okay, so are there any other questions?
Ma'am, what is the X1, X11, X12 exactly?
So this one, this is the, so what I said was X1, all these Xi's are in D dimensions. It's a, you need D numbers to represent them, right?
Uh,
So
So the
this is just,
superscript is superscript is the dimension and the subscript is the sample.
yeah, exactly. So
Okay.
this is, yeah, exactly, that's what it is. Right. Yeah. So I'm just trying to, say that what you have in terms of these x1 to xn, that still remains. That's the same thing, but you're just going to, instead of writing it as a in terms of the standard basis, you're going to write it in terms of, some other basis, some other orthonormal basis. Okay. So it's basically the same point, but written with a different representation. Okay. Any other questions? Is it all clear? Yes, no, you're all quiet. Yes. Okay. Okay, good. So let me just proceed with this. So what we'll do is now we'll find these U1 to UD. We'll take this view. So you want to minimize the error in the projection. So what we'll do is we'll just formulate this as an optimization problem. Okay. So xi for each of these endpoints, xi was the original point. Okay, it's this one, and this is the new point. So the difference between the two is the error. Okay. So what you're trying to do now is, what you'll do is minimize, you have endpoints, right? So I equals 1 to n, this difference xi minus xi tilde. It's a vector, so you just take its norm. Okay, norm square, and okay, it's an average error. So you take 1 by n times this difference. Okay, subject to, now remember xi, what we are going to use is in terms of u1, u2 up to ud. Okay, we are going to change this a little bit. And the problem is to find these vectors u1 to ud. Okay, so the constraints would be that these are orthonormal vectors. So ui transpose ui is 1 for all I, and ui transpose uj is equal to 0 for all pairs I not equal to j. For all pairs, okay, which are not the same, you have this constraint. Okay, so just to be more clear, so this xi, what we are going to write is this representation. So this is just going to be summation j alpha ij u j, and this one is going to be, so j equals 1 to d, and this one is going to be summation j equals 1 to k alpha ij ug. Okay, so that's why this is an optimization problem, and the variables are the u's, the vectors u1 to u, in fact ud itself. Those are going to be the variables to this optimization problem. So this is a minimization over u1 to ud. Okay, so yeah, so let me just write it in a little more clearly. So what you're going to get here is just minimize 1 by n summation I. So for each sample, what you're going to do is xi is just summation alpha ij uj. So j equals 1 to d minus summation alpha ij uj, j equals 1 to k, okay, square of this, subject to ui transpose ui equals 1 for I equals 1 to d, okay, and ui transpose uj equals 0 for I and j both are 1 to d, and I not equal to j. Okay, so so one thing is, the variables I said was the variables are just u's, so u1 to ud. Okay, so what about alpha? Is that going to be a variable? What do you think? Is it a variable, or is it something that's given to you, or how would we get alphas?
I'm given a basis, alpha is fixed because x is fixed. So
Yes. Yes, so that's exactly why alphas are not a variable to this optimization problem. So these alphas are just xi transpose ug. Okay, and the x's are given. Okay, so this is also xi transpose ug. Okay, so good. So this is the problem, and you can simplify this a little more. So if you look at the objective, here there are more terms. Okay, so j equals 1 to d, and here j equals 1 to k. Okay, so so these terms will just disappear from the summation, and what you will in turn have is you will just want to minimize I equals 1 to n. You are going to be left with just summation alpha ij uj, where j is now from k plus 1 to d. Okay, so this is the one that remains, and all these other constraints remain, such that u element of, let me call this set as omega, so u element of omega. Okay, so so you've reduced the problem in some sense. Now you can even further reduce it. So this is just so the objective is just summation j equals k plus 1 to d alpha ij uj. So this is a square, it's a norm square. So this transpose summation j equals k plus 1 to d alpha ij uj. Okay, so this is what we have, and so you're going to have all these cross products. So it's basically you will have all terms like u1 transpose u2, sorry, not u1, right? It's k plus 1 onwards. Okay, so just give me a second. Okay. So what the terms that are going to come are like uk plus 1 transpose uk plus 2 and so on up to all the cross terms basically, uk plus 1 transpose uk plus 1 uk plus 1 transpose uk plus 2 and so on up to uk plus 1 transpose ud. Okay, all these terms will be there, but these are all, you want these to be orthonormal, so these will disappear from the summation. Okay, so what you're going to have here is just going to be summation alpha ij square and uj transpose uj. Okay, so j equals k plus 1 to d. Okay.
So this you are writing only the norm term, right?
Yes,
This is just
yes.
the norm term.
Yes, just the norm term, only this part. Right, so the norm is just this summation, I mean this vector, transpose the same vector. And yeah, so all the cross terms which you have, any ui transpose uj, anything of that form, or uj transpose uk, or some things which are not equal, those terms just vanish because they are supposed to be orthonormal. Okay, and so what you're going to get is just these terms, and this is for every I. Okay, so objective is just going to be this. Okay, and in fact, this is also going to, you want these to be 1. So what is going to happen is you will just have I equals 1 to n, each of the samples, and j equals k plus 1 to d alpha ij square. Okay. So I don't know if it's been clear. So are there any questions on this? Is this clear how we got this as the objective? Yes. Okay. Can I also hear from some of the others? Yes. Yes. Okay. Okay. Good. So now again, the overall problem is just you want to minimize this quantity. So minimize this subject to those constraints. Now alpha.
There is a 1 over n still, I think.
Correct.
1 over n.
Yes, right. So yeah, thanks for pointing this out. So yeah, 1 by n times this double summation you want to minimize. Okay. Now again, as Siddharth pointed out, this alpha ij is just going to be xi transpose uj. Okay. So what I can write is minimize 1 by n summation I equals 1 to n, and summation j is k plus 1 to d. So xi transpose uj and xi transpose uj, it's a square of that. So what I will write, it's just the two numbers that I'm multiplying here. So what I will just write it in a slightly different way. So I will just write it as uj transpose xi and xi transpose uj. Okay. Yeah, so this is going to be the problem that I'm going to solve, subject to again all these terms like ui transpose uj equals 0, where ij in 1 to d, okay, and I not equal to j, and of course ui transpose ui equals 1 for all I in 1 to d. Okay, so this is the problem I get, and I will just take I'll just simplify this a little more. Like I can interchange these two summations. Okay, so what I can write here is, instead of in this manner, I can further write it as, I can write this objective as okay, let me write it here. So maybe, so j is k plus 1 to d uj transpose summation I equals 1 to n xi transpose uj. Okay, so it's just, I'm just changing the order of the summation.
The center term also has by n. I think that is also there, right? 1 over n.
1 over n. So okay, yeah, we can club this here as well by n. Right. Okay. So it's just I can safely interchange the summations here. This is not a problem, and then even the xi's. So I can club the xi term. So you can just take a simple example and see that these two are actually going to match. Okay, so yeah, so it turns out that these two are equivalent. So this matrix here, right? So this xi transpose, that's actually going to be a matrix. Okay, so xi is of size rd. Okay, and xi transpose, it's a row vector. So xi is a column vector and xi transpose is a row vector. So when I do xi transpose, what I'm going to get is a matrix of size d cross d, and I'm summing up n such matrices. Okay, so this part, this summation xi transpose. Okay, so I equals 1 to n. So 1 by n of this times the summation. This is what I will call as a matrix S. Okay, so this is actually given to me. These are the sample points of which you removed the mean. Okay, and so that is x. That I'll just call it as S. Okay, and one thing to note is immediately this S is positive semi-definite. Okay, because you can, I mean, this is one of the characterizations of positive semi-definite matrices, that you can write it as a sum of n rank 1 vectors. I mean, you can just write it as a sum of rank 1 vectors. Okay, so so this is positive semi-definite. Okay, so the problem now overall, it has become minimize summation j equals k plus 1 to d uj transpose s uj, okay, subject to again those constraints. Ui transpose ui is 1 for all I equals 1 to d, and okay, and ui transpose uj equals 0 for all I J pairs in 1 to D and I not equal to J. Okay, so this is the most simplified form of the optimization problem I get. Okay, so we will just see how we can use the ideas we learned in class to solve this. Okay, but before that, I just want to check these points clear. Are there any questions on this? How this formulation came or any of these simplifications? Are there any questions? Yes,
Can you
no.
go back a bit to that alpha where we rewrote the xi? Yeah.
This one? Yeah.
Oh,
So
that was alpha ij square, and just because like we just wrote it uh, xi uj transpose xi, that was just a
yeah, so
number. But,
this is a number. Yeah.
but
So
just because we rewrote it in a certain way, it became a like that is uh, okay.
so
It is still a number this way also.
yes, yes, exactly. So if you, I mean, we rewrote it this way, but now if you take this product here, okay. So suppose let's just take this term, okay, maybe
Oh, okay, yes, ma'am.
right. S is a matrix of size D cross D,
Yes, ma'am.
right? And Uj is a row vector, and I mean, Uj transpose is a row vector, Uj is a column vector. So overall, this is also going to give you the same number itself. Okay. Yeah.
So that number, Divya, if I may say, it is just like the average error.
Yes.
It's
Yes.
like the average error. Yeah.
Yes, it's exactly this term. What we started off with was this xi minus xi tilde. Okay, so it's exactly this same term that we are writing in a slightly different way. Okay, so these, because of the structure that because of these representations, we wrote it in this form. We expanded these xi and xi tildes, and here some things got cancelled, and so we had this form. Okay, so this was the error. So in fact, because you used only the first k vectors to represent in x tilde, so what happens is the error is the remaining terms, right? The terms from k plus 1 to d, alpha, ij, uj. So those terms are something that you are not capturing when you do the projection, and that is exactly the error. Okay, and that error we can write it in a slightly different manner, and that is in this form. Or if you take the summation xi transpose as one matrix, then you can just write it as uj transpose s uj. Okay, the summation of uj transpose s uj.
And that 1 over n makes it like an average error.
Yes, exactly. So this 1 over n has been absorbed into the s, and so overall it's an average. So you can think of it as the average error from each of the components that you didn't use in your projection. So uj transpose suj is like the average error because of not using the jth dimension. I mean the jth vector from the orthonormal basis. Okay. Yeah, are there any questions, anything else that you would like me to clarify here? Yes, no, is it clear? Like, many of you are very quiet. So, can you type if it's clear or if it's not clear, or ask if something needs more clarification? It's clear? It's clear? Okay. Okay, so fine. So now what we will do is let's just focus on this optimization problem. The variables are again the u's, and let's see what we can do. So first of all, let's just analyze this problem a little bit. So we said that the S is given to us, and that is a positive semi-definite matrix. Okay. So overall, what is your sense? Is this a convex optimization problem or is it not convex? Can I hear some thoughts on whether this is convex or not? So okay, let's go step by step. What about the objective? Is it convex? Is the objective function convex? So objective function is this, right? Summation uj transpose s uj. Is this convex function of the use? Yes, yes, okay, good. So this is the objective function is convex. That's right. Now, what about the constraint set? So let me call this
So the objective is convex because the second derivative is positive
positive
semi-definite.
semi-definite. Exactly. Right? Yeah. So convex because you can use this property. The second derivative is positive semi-definite. So Hessian is positive semi-definite. So now in terms of the constraint set, okay, so is this a convex set? So let's look at maybe let's just look at this constraint ui transpose ui equals 1. So I'll just say that it is h of u. So hi of u minus 1 equals 0. So that's the constraint. Okay, so or let me just say it's hi equals 0. Okay, so hi, it's of the form hi equals 0, where this hi is ui transpose ui minus 1. Okay, so is h a convex function?
Yes, ma'am, it's a norm.
Can you say again? I couldn't.
Yes, ma'am, it's a norm. So,
It's a norm, yeah. But one thing is, when you have hi of u equal to 0, such a thing, if it is anything which is, non-linear, then it's not going to be convex. Okay, so norms are convex. So if you had something like ui transpose ui was less than or equal to 1, yes, in that case, this constraint would contribute to a convex space. Okay.
So maybe if you can draw for x and y, if you draw like for 2 dimension, that becomes a circle, right?
Yes, exactly. Let me just maybe just draw that. So this equivalent constraint ui transpose ui. Let's just take ui it's in 2 dimensions. Okay, so like let's just say ui is some c and d. Okay, so what this constraint is telling you is c square plus d square is equal to 1. Okay, so that would mean this kind of it's exactly a circle. Okay, so this is the C and this is the D's. Okay, so it's everything on the periphery of the circle. So, the interior is not included. So, if you say this kind of a constraint, it's non-convex. Okay, even though this function C square plus D square is a convex function, but when it comes in the equality form, C square plus D square equal to 1, such a constraint will lead to the, constraint set being non-convex. Okay. Yeah, so I hope that's clear. So the only way when you have equality constraints in a convex optimization problem would be that, these functions are all linear. Okay, so something like, A times ui equals 1. Okay, so something like that, or A transpose ui equals 1. So something like that is going to be convex. It will give rise to a convex set, but anything else that you have is going to be non-convex. Okay, so this problem, because the constraint set is non-convex, this optimization problem is non-convex. Okay, so I hope this has been clear. Just stop me, okay, if something is not making sense. Okay, so this is a non-convex problem, and but still let's just try to give a shot at it. Okay, we still know how to characterize some things, like, okay, if you have some Kkt conditions, let's just try to find the Kkt conditions and see what they imply here. Okay, so remember that when you have for any general optimization problem, so we had these necessary conditions, right? So if you have these regularity assumptions, so we learned of something called regularity. Okay, so which said that if you take the the gradients of the active constraints. So gradients of the active constraints or the equality constraints. So in this case, there are no equalities. So gradients of, there are no inequalities. So you look at the gradients of all the equality constraints. Okay, and if they are linearly independent, then we say that such a point is a regular point. Okay, maybe let me just write it a little more clearly. So okay, so I think let me just retrace a little bit. Okay. Okay, so let's just say that this is the non-convex problem that you want to solve. And I'll just change the problem a little bit. Okay, so what I'm going to do is I'm just going to keep these constraints, the orthonormal constraints, the UI transpose UI equal to 1. I'm just going to keep those constraints and I will just ignore this for the time being. Okay, we'll just come back later and see what happens. But let's just look at a modified problem where I'm looking at minimize summation j equals k plus 1 to d uj transpose s uj subject to uj, yeah, so it's now ui, okay, so let's say uj itself, uj transpose uj is 1 for all j equals 1 to d. Okay, so I'm just looking at this problem, ignore this constraint. Okay, so for this problem, what I'm going to see is, can I apply the necessary and sufficient conditions that we saw? Okay, so here, if I look at the variables, okay, a way to represent the variables, one thing is the variables are all u1, if I can just stack them up, okay, so u1, u2 like that, up to ud. I'm going to get a long vector. So this is the set of all variables. So this is the set of all variables. Okay. Okay, and what I'm going to do now is I'm going to just check if, what are the regular points here. So the regular points means here there are D constraints. Okay, so let me just say Hj of U equals 1. So this is Uj transpose Uj minus 1 equal to 0. So that is this each of these constraints. So if I take the gradient, so gradient of Hj of U. Okay, if I look at this, what's going to happen is, corresponding to, let's just take j equals 1. So h1, gradient of h1 of u. So h1 of u is the constraint that u1 transpose u1 equal to 1. Okay, u1 transpose u1 minus 1 is 0. So now if I take any u, u which is, a point, any set of u's that I take, okay, so any set of points, if I take the gradient here, what I'm going to get is just 2u1. Okay, so what this would mean is that the gradient will look like something like this. So 2u1, so that would be the first set of D numbers. Then after that, there is no element of u2. So all these are 0. So this is some D numbers which are all 0. Now again, for u3 also I'm going to get zeros like that. And so all these are going to be 0. Okay. Now if you take gradient of h2, what is going to happen is here you will get all zeros because the gradient is just going to be 2u2. So gradient of h2 of u, so that if you take, you're just going to get 2u2. Okay, so this will be 2u2 here. Okay, and all these are going to be zeros. Okay, so like that you will get so on, and for the last constraint you're going to get 2ud here. Okay, and everything else is going to be 0. Okay, so you can see immediately that these gradients are going to be linearly independent always. Okay, because of this form. So only, you have this kind of a block structure here. Okay, only some parts of it are going to take non-zero values, and these are going to be different components are going to be non-zero in all the vectors. And the only case if these are linearly dependent would be if all these u1 to uds are zeros, and that is not going to happen because the constraint is like this. Okay, so what we have verified here is that every every u. Okay, so every u here, every u which is feasible for this problem is every u which is feasible is regular. Okay, and so because of that, what it means is that, we have this necessary condition which says that, if you have the optimum point to this problem, it will satisfy the Kkt conditions. Okay, so optimum u star. Okay, so the optimum u star is going to satisfy Kkt conditions. Will be Kkt conditions will satisfies Kkt conditions. Okay, so that's one thing we'll check. So what this means is that you can narrow your search to those which satisfy the Kkt conditions. Okay, so are there any questions here? Is this clear, or is there something you would like me to clarify, or am I audible?
Get that
Yes.
linearly independent part.
Okay, so so let me just do a brief recap. So are you okay? So I hope, we are kind of running out of time, but I'm willing to spend some more time to explain this. Okay, so is there any class afterwards, Siddharth, for the undergrads?
No, ma'am.
Okay, so what about the masters? Are there? Do you have any class? So who is? Okay, no. Okay. Okay, you don't have any class. So I'll just take some more time to explain this. So what I'm doing here is, okay, let's just count first the number of variables. Okay, so the variables here are u's. Okay, so the vectors u1 to ud. Okay, these are the variables. Okay, so each of them has d components. And so the total number of values that you need to find is d square. Right? So U1 has D components, U2 has D components, like that. So totally there are D such vectors. So there are D cross D, that many numbers that you have to estimate by solving this optimization problem. Okay, so what I'm just trying to do now is to apply some of these regularity conditions that we saw in constrained optimization. Okay, so if you remember, what we did there was, let me just do a small recap maybe. So earlier what we had is, we had a function minimize f of x subject to, let's take the case where you only have equality constraints. So you had hjx equal to 0. Okay, so here x's were the variables. So let me just do a small recap. Okay, so here what we did was, for a regular point, what you wanted was, a point x was called a regular point if you took the gradients with respect to x. Okay, so there are some j equals 1 to capital J. Okay, so many constraints were there. So you compute gradient of h1, the first function, gradient of h2x, like that you took. Okay, and you take gradient h capital J of x. Okay, and you want these set of vectors to be linearly independent. So that's when x is a regular point. So the gradients evaluated at a point x, if those are linearly independent, that was what we called as a regular point. Okay, so the necessary condition was that, if x star is a regular, so the optimum for this optimization problem, if x star is a regular point, and if x star is optimum, okay, then what you had was, x star will satisfy the Kkt conditions. Okay, so so this was the statement that we saw at that point. Okay, and so what this meant was, if you find the Kkt, suppose you find all the regular points, and then out of that you're able to find some of the Kkt points, that gives you a way to look for the optimum. So one of these will be the optimum. Okay, so so I'm just trying to use this idea here. So I'm just trying to see what are all the regular points. Okay, so suppose the entire set of feasible points are regular, then what I can do is I can just find all the KKT points, and out of them I can choose the one which gives you the best. Okay, which gives you the best value, because anyway I'm guaranteed that since all the points are regular, and if x star is optimum for all the optimum points, they will appear as some KKT point. Okay, so that's what I'm just trying to do here. I'm just trying to see which are all the regular points. Okay, so to do that, so remember here, what we did was you take all the variables, right, x. So in this problem, for the PCA problem, the x actually means this is the value of x. I mean, this is what would take up x. So all the variables you have to collect together. Okay, so it's u1, u2, and so on up to ud. So those are d vectors, and each of them has d components. So this is the first d components, and this is the next set of d components, and so on. So the total, this is a vector of size d square. Okay, so the d square variables, and this is the collection of all the variables. So now what I'm going to take is I take each constraint and I'm going to evaluate the gradient. Okay, so the gradient of this h1u, I'm going to evaluate the gradient with respect to all these variables. Okay, so in terms of h1, the first constraint is u1 transpose u1 is equal to 1. So if I take this constraint, the gradient is just going to be 2u1. With respect to u1, it's 2u1. With respect to u2, the gradient is 0, and so on. So 2u1, 0, 0, 0, like that I will get for the first constraint. And similarly for the second constraint, it's just 0, 2u2, 0, and so on. Right? So u2, so the second constraint is u2 transpose u2 minus 1 is 0. Okay, so like that, if I do, the vectors which I need to check whether are they linearly independent is this collection. So 2u1, 0, 0, 0, 0, 2u2, this one, and so on. Okay, is this clear?
Ma'am, but you said that variables are the ones like inside that. So even every component of each vector is a variable.
So every component of u1, so u1 is a vector, every component of u1 is a variable, right?
So when we are taking the gradient here, like we are with respect to what are we taking the gradient then?
Yeah, so the gradient is with respect to all the variables, right? So if you have this constraint, so each of these constraints involves only one variable at a time. So the first constraint only involves u1. So it involves only the first d components. The second thing only involves the next d components, and so on, right? Siddharth?
Yes, ma'am. But like if every component is a variable, then shouldn't we take with respect to each component separately?
Yeah, so what we are doing here is we are exactly taking with respect to each of the components. So there are d square, total number of variables is d square. Okay, and when we take the gradient, we are taking actually the the gradient with respect to each of these d square components. That's exactly what we are doing. So each of these gradient vectors, this is a vector of size d square. This is going to be a vector of size d square. Okay, but what you see is that the first constraint only involves d terms, right? So that the first constraint u1 transpose u1, this will involve only these components, the 1 to d, the first d values. It will only involve that. Okay, so when you take the gradient with respect to all the u's, so if you take the gradient with respect to u1, you will only get 2u1. Okay, do you agree with that? So the gradient of this constraint with respect to the first d variables, u1, whichever is then u1, that is just going to be 2u1. It's a vector 2u1. Is that okay?
Yes, ma'am.
Okay, so with respect to u1, you're going to get 2u1. Now with respect to u2, u2 doesn't show up anywhere here, right? So you're going to just get 0, right? And with respect to, so this part is just gradient h1. So this is, let me just write it clearly. So gradient of h1 with respect to u1. Maybe u1 is a vector, right? So it would just be gradient of h1 with respect to u1. And this part is gradient of the the first constraint with respect to u2. And the last one is here gradient of h1 with respect to ud. Okay, so this is some d numbers which are 0. Here again another d number, set of d numbers which are 0, and so on. The only thing which is which could be non-zero is this first d vectors which represent u1, which represent the gradient with respect to u1. Okay. Is it clear, or there?
Yes, ma'am, it's clear now.
It's clear. Okay, so the idea is, so what I'm trying to get at is, every point you take here, every feasible point here, if you take any u that you take, any collection of vectors u1 to ud that you take here, which satisfies uj transpose uj is 1. As long as it does that, what you're going to get is, this point is going to be regular. Okay, so all the points in this problem are regular points. So you can just focus on the Kkt points now. Okay, you can try to focus on the Kkt points and then find the best Kkt points. Okay, so that is how that is, and that is going to give you the optimum. Okay, so let's maybe just try to find the Kkt points here. Okay, so okay, maybe I should just, there's a lot of clutter here, so I'll just write it in a new page. So the problem is minimize summation uj transpose suj. Okay, so j equals k plus 1 to d. Okay, subject to, so I'm looking at a smaller problem where uj transpose uj equals 1 for all j. Okay, so now what we're going to do is we're just going to find the Kkt points. Okay, so here what I will do is I'll just include Lagrange multiplier mu j for each of these equality constraints. So the Lagrangian is a function of u and mu. Okay, so yeah, so let's just write, maybe let me just call it lambda so that avoid some confusion. Mu and mu look similar, so u and lambda. Okay, so lambda of, the Lagrangian with respect to u and lambda. So this is just going to be summation uj transpose suj. So where j equals k plus 1 to d plus j equals 1 to d. Okay, lambda j uj transpose uj minus 1 minus, so lambda j times uj transpose uj minus 1. Okay, let me write this properly. Okay, so this is the Lagrangian, right? So now what you have to do is to find the Kkt points, gradient of the Lagrangian with respect to u is 0. Okay, so let's just take each of the components. Let's just try to take with respect to uj's. Okay, let's just take with respect to uk plus 1 up to ud. So with respect to uk plus 1 to ud, let's just try to write this. Okay, so what this will give is, can we take the gradient with respect to, say, uk plus 1? So what's the gradient? Can
Half
somebody...
of suj plus, so summation half.
Yeah, so with respect to just uk plus 1, so this term is just going to give you
Half of suk.
So it's half, is it? So it's half or 2 times?
Oh, sorry, 2 times.
2, yes, 2 times suk plus 1 is just going to give you, okay, 2k times suk plus 1 plus this part
Lambda
also.
uk plus 1.
Yeah, so plus 2 times lambda uk plus 1. Sorry, what am I writing? So lambda j, so lambda k plus 1,
Plus 1, UK plus 1.
uk plus 1 is 0. Okay, so what this will give is suk plus 1 is equal to minus lambda k plus 1 uk plus 1. Okay, so lambda has no sign restrictions because these are all equality constraints. So you can immediately recognize this. Can you say something from this form? What would lambda and u be?
Eigenvalues and vectors.
Exactly. So lambda k plus 1. So lambda k plus 1 is an eigenvalue. And so lambda k plus 1 and yeah, uk plus 1, lambda k plus 1 is an eigenvector value pair. Okay, so eigenvector and eigenvalue pair. Okay, so that's going to be the case with everything from k plus 1 to d. So same thing, you will get u k plus 2 is going to be some minus lambda k plus 2 u d plus, sorry, uk plus 2. So like that you will get, and so all these u's turns out that these are going to be the eigenvectors. Okay, so now which of these eigenvectors should you take? Okay, so I mean, I can ignore this minus sign because anyway these lambdas are going to be, there's no sign restrictions, so I can just ignore this minus sign. Okay, so one second, so just give me a second. Okay, yeah, so yeah, sorry about that. Okay, so yeah, so what the takeaway here is that the eigenvectors and the eigenvalues are what is going to give you the answer to this optimization problem. Okay, and in particular you want this overall objective for these k plus 1 to d, those terms should be as low as possible. Okay, so now if you substitute this value in terms of the objective, I mean, we also have this u1 to uk, we'll just come to that in a minute. So these are eigenvectors and eigenvalues. So which of these eigenvectors and eigenvalue pairs should you take, right? So in terms of minimizing the error, this quantity has to be minimized. So if you substitute the value of the objective, okay, with these eigenvalue pairs, what you're going to get is j equals k plus 1 to d. So uj transpose s uj. Okay, so now because suj is an uj is an eigenvector, so what you're going to get is this is going to be lambda j uj. Okay, and so what you're going to get is j equals k plus 1 to d lambda j uj transpose uj. Okay, so I'm just ignoring the negative because or you can keep it also. So but anyway, the idea is you want this objective to be as low as possible. So where lambdas are the eigenvalues, okay, and uj is the eigenvector, and you can choose the eigenvectors which with unit norm. Okay, so this value is 1. So in terms of minimizing the error, this lambda k plus 1 to d, those have to be as small as possible. Okay, those have to be the minimum eigenvalues. So in general, the first d, so k plus 1, so lambda k plus 1 to lambda d, these have to be the min eigenvalues. Okay, because those are the ones which minimize the error to the extent possible. And so uk plus 1 to ud are also the corresponding eigenvalues. So now, since you remember, like the original problem was to find, you also needed to find u1 to uk. Okay, so we ignored this constraint, right? U1, ui transpose uj is 0, and you also have this 1 to k there. And so what you can do is you can consider all the eigenvectors of S. Okay, and if you take the largest eigenvalues, so lambda 1 to lambda k, the top k eigenvalues and the eigenvectors corresponding to that is going to be the u1 to uk, and it will implicitly satisfy this constraint that the eigenvectors are orthonormal I mean, they are orthogonal to each other because this is a real symmetric matrix. Okay, so maybe I will just spend some more time tomorrow to complete this because I think it's quite into the time. I've taken up quite a lot of time. So maybe let's just come back to this again tomorrow. I will just summarize this and maybe clarify any doubts that are there. Okay, so yeah, so I don't know if this made much sense to you all. Okay, so I just hang back for maybe 5 minutes. So thanks for being here today. We'll again meet tomorrow at 10:30. Okay, so, yeah, thanks.
Ma'am, why was it okay to ignore the minus sign? I didn't understand at the end.
Yeah, so here, so I think I kind of went a bit too fast in this part. So what we were saying is, okay, so this is a negative lambda k plus 1. So instead of just, lambdas there's no constraints on the sign, right? So let me just call this something like it's negative lambda. Let me just call it something like mu k plus 1. Okay, so it's as if, these are...
But S was positive semi-definite.
Yes, S is positive semi-definite, right?
Why are we getting a minus sign here?
So the minus sign...
Because lambdas are unrestricted, so
yes, lambdas are
the
unrestricted.
eigenvalues are greater than
yes, yes, exactly.
Okay.
So ultimately, whatever is going to satisfy this is going to have that minus lambda. It's going to be greater than or equal to 0. That's going to be the case. Okay.
So, ma'am, then lambdas are going to come out to be less than 0.
Lambdas are going to be?
Less than 0.
Why?
Because S is positive.
Oh, this thing. Because, I mean, yeah, when you take it as minus lambdas, it's going to be, yes, lambdas will come out as less than 0. True.
So, ma'am, when we put it in the actual minimization, our objective function, that time also we'll be considering the eigenvalues or the negative of the eigenvalues.
So if you take, okay, let's just go ahead. I mean, let me not confuse it with this mu k. So let's just take it as though we have only lambdas. So suj is now going to be minus lambda j uj in terms of what we have written, right? And so this is going to be minus lambda j uj transpose uj. And these lambdas, this minus lambda j is going to be greater than or equal to 0. Right? Because
Yes, ma'am.
this was positive semi-definite, so this is going to be greater than or equal to 0. So in essence, what you do is, okay, so minus lambda k plus 1 to minus lambda d. I mean, you want to minimize this, so you choose the minimum eigenvalues. So minus lambda k plus 1 to minus lambda d are the smallest eigenvalues.
Okay.
Right? Yeah, maybe I'll just clarify this again tomorrow. So I went a little bit fast here. So.
Ma'am, I also had a doubt. In the initial stage, we have two constraints, and we said that we have relaxed one of the constraints and did all our calculations in that a point, that is the point is regular or not. Now, is it okay to do that? Because for checking a point regular or not, we have to create all the constraints.
Yeah, so what we are saying here is now we are considering this problem. I mean, it's a relaxed problem in some sense where you don't have one of the constraints. Now, what we are going to do is for this problem, we have an optimum solution. We're going to do all our computations, find the optimum for this problem. And then we're going to show that that optimum also satisfies the other constraint, which we ignored. Okay, so then in that case, it's fine. I mean, your ultimate objective is to be able to find the optimum solution. So you work with a relaxed problem and somehow the optimum turns out to also satisfy the original constraints. I mean, you ignore regularity and all that, that is fine. But as long as the final optimum also satisfies those constraints, you're fine. Right?
Okay, ma'am. But in general, for checking regularity, we should consider all the constraints, right?
Yeah, if you don't have, so the reason here, what we're doing is we're kind of going a little back, a step behind, in the sense that, if you put in those constraints, there's probably some difficulty in, computing the Kkt conditions and all that. Okay, so what we're doing is we're simplifying the problem a little bit. Okay, and for the simplified problem, we are computing, so that is fine. But yeah, if you don't, if you avoid some constraints and still it doesn't simplify, or still the optimum doesn't satisfy the other constraints which you ignored, then there is a problem. Okay, so you cannot do that. So in effect, like whatever constraints you are considering, yes, for regularity, you should consider all the constraints. That's true.
Okay, ma'am. Okay.
Ma'am, on the last point,
Yes.
but isn't it like we're taking our x to be fixed, like in some sort of a set that is constrained itself? So like we did in class, we didn't assume x to be RD. We took greater than equal to 0, so we didn't have to add a lambda for both the conditions.
Yes, exactly. Yes. So many times this is something which is done because the more constraints you have, sometimes the problem becomes harder to handle. So you try with a smaller set of constraints, and if it anyway satisfies the optimum, if it satisfies those constraints which you ignored, then it's fine anyway. Like even in general, ideally, if you ignore all these constraints, even you could start by ignoring this, right? Uj transpose uj equals 1. Why have that? So if you solve this unconstrained problem and then it turns out that it satisfies these constraints, then it's even better. Okay, but if you ignore even these constraints also, what you're going to get is an unbounded problem, right? Possibly uj transpose suj, you're just trying to minimize a quadratic function with no constraints like this. So may not get the thing that you want. May not satisfy these constraints finally. Okay, so that's why you first start off by keeping as few constraints as possible, and then try to see what happens.
Ma'am, actually, just on a linear algebra note, isn't that objective function a norm in itself? It's one of the norms we studied during math class. I think it's called the
Yes.
one norm or something. And then in
This
that
one,
case, it's
right? This uj transpose
yes, ma'am.
suj. Yeah, it is a norm with respect to this matrix S, right? So if you had S as identity, then you're going to get the regular norm. If it is some matrix S, then you're going to get it is a norm, but with respect to a matrix.
Yes, ma'am. The matrix norm. Yes, ma'am.
Yes.
Okay. Thank you.
Yeah, so there are different ways to approach this problem, but this is just from the lens of an optimizer, how you approach this, right? Yeah, Siddharth, you wanted to ask something?
No, ma'am. It's clear.
Okay.
Ma'am,
Yes, Lakshmi.
so the constraints which we prove whether it was non-convex. So if you apply the second Hessian first, if you apply that way, it is positive definitely. So how I understand that it's a if you take, because it is in the form x square plus y square is equal to 1, it is convex. But if someone does it in the other way, if you apply that the
Second
Hessian,
derivative?
so then that is coming out to be positive definitely.
Yeah. So what is happening here is this function h is a convex function. Okay, that is true. So if you take the second derivative of this, you will get you will get a matrix with 2's over there. So that is, of course, these h's are convex. Each of this function on the right hand side, this is convex. Okay, so but the issue is, if you have a convex function equal to 0, then the set of points which satisfies it, that set is non-convex. Okay, this function h of u equal to 0, this h function, this is convex. This function is a convex function, but the region, the space of u's which satisfies h of u equal to 0, that is not a convex set. It's the two things, convex function and a convex set here. The set of u's such that hiu equal to 0, this is non-convex, even though h is convex.
Also, do you have time?
Tell me, I have a meeting which started at 3, but it's okay. Tell me.
I had a question in regularity. I understand that if there are multiple constraints, then we check the linear whether they are linearly independent, and we say that the point is constraint. But if there is only one constraint, how do you check?
So if there's only one equality constraint, right? So if there's only one equality constraint, it is the regularity assumption is satisfied as long as you don't have zeros. Okay, so let me just put it here. So this, right? So something like minimize f of x such that h of x equal to 0, right? So here the only gradient that you have is, this is the only vector. Okay, so gradient of h of x. Okay, so if this is so this set has to be linearly independent. So what it means is that these are all not equal to 0. So as long as if this is not equal to 0, then x is a regular point.
Okay. Why is it only for equality constraint?
No, it's also for inequalities also. So suppose one more thing. So if you, same thing, even if you have minimize f of x such that h of x less than or equal to 0, same thing. I mean, here also, yeah, it's the same thing holds here, same condition. So gradient of h of x cannot be equal to 0.
Okay, thank you.
Yeah.